Hi everybody, it's Mrs. Mancuso, and we have been talking about electrochemical cells. And electrochemical cells are where redox reactions happen. There's two types. Last week we did the first type, which is voltaic cells, and those are the ones that are spontaneous. And so those are the ones that produce energy. So when they produce energy, they are converting chemical to electrical energy. So we had our two containers, we had our pieces of metal, they were connected by a wire, there was a salt bridge. Sorry, this is a terrible diagram. But as the electrons went through the wire from the anode to the cathode, those electron movement produced energy. So a great example of a voltaic cell is a battery because it provides energy for you to do something. The kind of reaction and the kind of electrochemical cell that we're going to focus on today is called an electrolytic cell. So an electrolytic cell is not spontaneous. If it's not spontaneous, it will not work without energy. So it needs an input of energy. So it either needs to be plugged in or it needs a battery attached to it. So it needs something to give it power. So I like to say that during the day, your cell phone works because it works like a voltaic cell and it uses the battery for power. But then eventually it dies. So at night, it does the other reaction, which is non-spontaneous, and gets the potential back to be able to work. So at night, while it's charging, it's doing the electrolytic reaction. So I'm going to draw out what it looks like. So this time we are just going to have one container, and this time we're going to connect it to a battery. So I'm going to have still two electrodes in here. But this time I'm not going to focus so much on the metals. Instead, there's two really typical types of electrolytic cells. This time my battery is connected to these leads, and here is my negative and here is my positive. Now, in the past, we know that positive has been a cathode, but when there is a battery, it changes the charge and it forces this non-spontaneous reaction to happen. So this time my positive is going to lead me to my anode, and my negative is going to lead me to my cathode. So that's one way that you can identify it immediately, because very often these little leads or electrodes do not have specific metal names attached to them or metal types. So instead, we're more worried about the solution, or we're more focused on the solution. So let's say the solution is copper 2 chloride. The reaction of copper 2 chloride decomposition would produce copper, and it would produce chlorine. And chlorine's diatomic, so I have to put the 2 there. So it's actually all balanced. Now, this reaction, this was a +2, and now it's a 0. This was a -1, and now it is a 0. So what is being oxidized? The Cl. Cl2 at -1 becomes Cl2 plus 2 electrons. And then what's being reduced is the copper. Cu plus 2 plus 2 electrons makes Cu. So that is weird because my metal would normally be oxidized, but this time it's being reduced. So that is definitely not spontaneous. And my nonmetal would like to be reduced, but in this case, it's being oxidized. So I know that this reaction definitely would not happen normally. The only way you can make this reaction happen is by connecting it to a battery. When you connect the battery, Oxidation always happens at the anode, and reduction always happens at the cathode. So anox, red cat, still exactly the same. So I'm going to go to where the anode is, and I'm going to show chlorine gas forming there. So here I would have chlorine. I know it's a gas, so I'm just going to show little bubbles. I wish we could be doing this in the lab right now because it's super cool. You see the bubbles forming at this little alligator clip here. We connect little pencils to it. And the bubbles, if you waft the air, it smells like a pool. So you know that you're forming the chlorine gas there. And then at the cathode is where we form copper. And again, this is super cool. You actually see all these clumps of copper forming here. So this is where the copper formed. So what's actually cool is copper is a positive ion. So the positive ion is attracted there and forms these atoms of copper. And you actually see it like this big clump of copper attaching onto here. So that is my reaction, and that is where everything occurred. Now, there is a second type of electrolytic cell, and this one, the example is called plating. So this one was called electrolysis. That was my example, electrolysis. So electro means use the electricity. Lysis means split. So I was trying to split copper chloride, and in order to do that, it was a non-spontaneous reaction, so it required this energy. I was using electrical energy to make a chemical reaction happen. That's the opposite of what a voltaic cell did. All right, now my plating example. So I know you've heard of plating jewelry. You can also plate like spoons or forks or whatever you have. So I'm going to draw a little spoon here. And let's say I want to plate it in gold. I need a gold bar here. I connect both of them to my battery. And then in order to label it, again, I could do the pluses and the minuses, but I'm going to tell you right now, this is the one that I want to get fat. So this is my red cat. So this is my cathode. By getting fat, what I mean is I want to cover this in gold. So if I want to cover it in gold, this has to be my red cat. A cathode is normally positive, but as soon as I see the battery, change the charge. All right, so instead of being positive, this is going to be negative. So follow it through and mark negative. And then positive, positive. This is my anox. Okay. The anode is where oxidation happens. So this is going to lose electrons. So I'm going to show the electrons going through the wire. And they would go back through this way. And I'm also going to show the thing that oxidizes falls apart. So I'm going to show the Au plus 1 over here. Then I'm going to show that this Au plus 1 is what forms my red cat getting fat. So if I had to write the half reactions, I'm not doing electrolysis like I did last time. I'm actually, my oxidizing is Au becomes Au plus 1 electron that went through the wire. And then the reduction for plating is the exact opposite. Au plus 1 plus the 1 electron coming through the wire makes gold. Now, if you really figured out what the spoon was originally made of, it's probably some metal like iron, which is definitely higher than Au on the table, which means it should get oxidized. But again, this is going to be a not spontaneous reaction. It only happened because I had the battery. All right, let's do a couple more just for practice. So I'll do another electrolysis one, which means that I want to separate out what I have in the solution. So let's do NiCl3. I have my 2 electrodes. I connect it to a battery. The battery has a positive. The battery has a negative. Normally, positive means cathode. So right away, I got to write anode because I know the charge is changed. And my anode is where oxidation happens. So this is going to lose electrons. So I show the electrons going through the wire. Then over here, this is negative, which normally is an anode, but because of the battery, I know it's reversed. So this is my cathode. This is where reduction happens. Then I actually do the decomposition reaction. NiCl3 would form nickel and chlorine gas. To balance that, I'd have to have 3 to give me 6 chlorines. Put a 2, that gives me 6 chlorines, and a 2 there. All right, write my half reactions. This is a +3, this is a -1. You're alone, so you're 0. So 2 Cl3s at -1 becomes 3 Cl2s, plus I would have to lose 6 electrons. The reduction, 2 Ni plus 3s plus 6 electrons would give me 2 Nis, because it changed by 3 times 2 atoms. 3 times 2 is 6 electrons. Okay, reduction always happens at the cathode. So I go up to the cathode and I show nickel. So this is where nickel would form here. And that means my chlorine, Cl2, is going to form there. All right, so I did all my steps. I wrote my half reactions. I have the electrons going through the wire. And let me do another plating example. So let's say I'm plating a ring that I bought from Claire's. All right, and let's say this time I want to coat it in silver, Ag. I connect the wires to a battery. Right away, whatever is being plated is going to get fat. So that's my red cat. And I have to have arrows going to it because I want to plate it. I want to cover it. This is going to get oxidized. So this is my anode. Ag becomes Ag plus 1. The thing that's oxidized loses electrons. So I'm going to have my electrons go through the wire here. This is positive because normally an anode is negative, but I want to reverse the charges because I have a battery. And then I want to have my electrons go through the wire. This is my negative because it is my cathode. I write my half reactions. So the oxidizing happened right here. So Ag becomes Ag plus 1 electron. And then the reduction is always the opposite of it. Ag plus 1 electron gives me Ag. All right, so my final summary of this. Electrolytic cells versus voltaic cells. Let's just do a little comparison chart. This one needs energy. It needs either a battery or it needs to be plugged in. And that's because it is a non-spontaneous reaction. You definitely notice the battery in the picture. That's one of the easiest ways to recognize the reaction. Here, the anode is positive and the cathode is negative, but the anode is still where oxidation happens and the cathode is still where reduction happens. There's 2 types of electrolytic cells. The first is electrolysis, and that was where I was splitting my compound, and the second was plating. They both are easy to notice because they both happen in one container and they're both connected to a battery. All right, over here on the voltaic side, this produces energy. That's because it is a spontaneous reaction. So it uses a chemical reaction and uses the chemical energy to make electrical energy, whereas electrolytic did the opposite. My anode was negative and my cathode was positive. This is my oxidation and this is my reduction. So the only thing that changed was the charge. And this always had 2 cells, and it always had a salt bridge. That was a unique characteristic that I always noticed. All right, thanks for joining me, and make sure you remember that every Friday I do a Zoom. So if there's something that you do not understand, it's a great chance to ask me questions and go over things. You can ask me questions anytime though. Just message me on Schoology and I would be happy to talk with you. I can also do individual Zooms. So if there's something that you're not understanding and you just want to see me face to face and go over it, just let me know. Bye guys, miss you.